Hello everyone. Can you hear me? Great. Great. Okay, good. Um, okay, so first of all, our first intro assignment, right, or coding assignment is for today, right? So today is the due date, right? Again, you obviously have um, three extra late days, but remember, it's maybe better if you can maybe wait for using those for the next assignments. But yeah, and in the end, you decide, right? So I hope you had fun with that assignment. I know some people were like probably very frustrated, or yeah, of course, Marvin. Yes, you do have time for finishing. Yeah, it's until midnight. Yeah. So yeah. So it's not right now, right? The due date is today, but at midnight. Yes. Okay. So the thing is, I hope you could enjoy the intro assignment. Of course, this course is challenging, right? And the coding assignments are challenging. They should be, right? And they could be yeah, frustrating for some people, but you need to develop like um, the ability to enjoy frustration or enjoy not knowing how to solve problems, right? Because that is what you will probably do in the future, right? And also I think there were a couple of people asking about the like if we will give you resources for the creative part, right? I think some people ask about it, and I'm already answered on Piazza, but I wanted to tell you something. So in that sense, what it usually happens is that if I give a list of like ideas or possible stuff or resources online, right? I mean, you can obviously Google it, right? But if I give you those things, what usually happens is that students tend to replicate or almost replicate ideas from other people, right? And those other people use their creativity to come up with interesting effects or interesting experiments. So in this case, we want you to experiment. We want you to create something new from the math that you already know, right? So yeah, so we will not give you for these creative sections on the on our coding assignments. We will not give you like many resources. Of course, again, you can search online, but yeah, keep in mind that you need to again to use your brain to come up with interesting things, and that's also like the part that you should enjoy the most, right? You can do crazy experiments, and don't worry, I mean, some of those experiments, maybe the result maybe is very very weird, right? I mean, and you might still have points for the creative part even if your result is very weird, if what you accomplish or what you try to do is creative and interesting, right? And of course that will depend on how we decide that, right? But yeah, but we love seeing people like to experiment and do crazy stuff, right? And boy say boy is saying the weirder the better. Not exactly like that, Paul, but yeah, kind of, right? Again, you need to experiment. And also something that is very important is that you eventually will you will like go to a company, for example, to maybe ask for a job, right? I mean, you might become your own boss, right? Maybe you will create your own company, but for many people these type of projects will be like part of your portfolio to show to someone, right? So what do you want to show? You want to show the same exercise that hundreds of students are doing exactly the same thing like year after year after year at UBC or in on other universities. I mean, the same very cool thing that everybody finds on internet that everybody is replicating, or your own super original stuff, right? I mean, yeah, usually it's way better to show something that nobody has seen before. Okay, so so today we have camera projections. We have these learning goals for today. Give me a second. So we will talk about the camera transformation. which is related with something called lookat transformation. We will also use that, this concept of lookat transformation, we will also use it for the inverse kinematic. Remember that I still have the pending stuff of recording you an extra session for inverse kinematic, right? I mean, conceptually speaking, you already know what it is. We already had that session, but I will give you more data and more insights for you to eventually accomplish the bonus points. And when, very good question. My plan is to record it today. I've been swamped with a lot of work, and actually today is not a very good day for me. Maybe if you hear that I am kind of like talking slower today, is because I have a huge headache right now. So I will ask for your patience. So yeah, today I will, my brain is not functioning correctly, but hopefully after the lecture today and maybe a couple of hours later, I will, I'm planning to record that session. So I will probably upload it either today, very, very late, or maybe tomorrow. Okay, so we will talk about lookat transformation. We will talk about how to basically having all that transformation, how can we get coordinates from the world to camera, right? How to translate from world to camera. And again, thank you so much. People is saying that that I should feel better soon. Thank you so much. And okay, so I will try to not read the chat too much unless I'm asking you questions, and we will have a couple of pauses, and you can raise your hand. Okay, so basically what we will study today and also on Wednesday and in the following lectures is how can we get the information that we have already in 3D, how can we convert it into 2D, right? Because in the end, we have 3D models and splines and things, and right, we have a lot of information, right? But everything is in 3D, but at the end, everything needs to be converted into a 2D image, right? Into a flat image that you can show in your monitor, right? So in some sense, you already know how that is achieved, right? Because we already studied the entire pipeline, and you know that the very last part of the pipeline is when we finally paint pixels, right? But now we are studying the math that is involved inside all those parts that we already conceptually study on the pipeline, right? So this is the part of the pipeline that is basically controlled by the vertex shader, right? So remember that one of the main goals of the vertex shader is taking all the information from your scene, right? All the vertex data that is obviously in 3D, and basically transform that data into screen coordinates, right? So you can then compute the fragments and discard geometry, discard fragments, and blah, 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 right? Everything else. Okay, so there are 3 things that we need to perform in order to make this transformation from 3D to 2D. So the first is a camera transformation or an eye transformation. That is what we will actually do today. So that is actually our session today. And basically, this what it does is that places the camera at an origin, at a certain position, right, in a convenient orientation, and depends only on position and orientation of the camera. This is basically like treating the camera as another object in the scene and computing its position and orientation, right? So we will treat the camera as an object, right? So we have a scene, we can have cars and buildings and whatever and characters. Well, the camera is just another object, right? So that is the first thing that you need, right? The camera transformation. Then after the camera transformation, we need a projection transformation. And this basically projects points from the camera space. All the points that are visible from the camera space to a range from -1 to 1 or on X and Y. And this depends only on the type of projection desired. And what I mean with this is there there are many types of projections, but in general, we have two types of projections, orthogonal projections or perspective projections. We will obviously talk about that later. Yeah. Okay, good. So the thing is, once we can convert the information that we have in world coordinates into the camera coordinates, the projection transformation, what it does is it basically creates these clipping sections and this frustum, right? If you remember, we already saw that. We already saw the frustum. That is like a truncated pyramid that is like the projection of the camera, the visible section from the camera. And we will use that to discard, for example, to discard geometry with clipping, right? And yeah, so basically that is the projection transformation. And again, it depends if it's an orthogonal or perspective projection. And the third need to use that we need to do is a viewport transformation or windowing transformation, that basically once you already have all your data, right, that it was in world coordinates, then it was it was transformed into the camera projection or the camera coordinates, right, and then it was it's basically flattened into the screen coordinates, right. So the thing is, depending on what are you rendering, right, the actual coordinates of your image can change, right? Because I can I am rendering something in 200 by 200 pixels, or I can render something in full HD, right? In 1080 by 19, I think it's 1920. Yeah, no, 1980 for time. Yeah, exactly. So depending on the size of the image that you are rendering, right, is the ratio of your image and basically the amount of pixels you have on the image, right? So the last part, this viewport transformation, is basically now converting everything that is already 2D and is already flat, but is in a very specific type of coordinates that are basically like a unitary coordinates. Everything will be in X and Y. Everything will be in coordinates from -1 to 1, okay, in X, and from -1 to 1 in Y. And basically you need to convert now that into the actual number of pixels that you already that you are computing, right, that you are actually rendering. Okay, so let's start with this camera transform. Okay, so consider a scene like this, right? So we have a world, right, which is represented by this grid, and the center of the world is basically the cross, this black cross, right? So that is the 0, 0, 0 of the world. And we have a couple of objects. We have 4 boxes. Imagine that this could be, for example, an OBJ. Maybe it's the same OBJ, right? An OBJ file that has obviously coordinates for these vertices and all that stuff. And we're basically loading that OBJ 4 times and applying a certain transformation, a certain scale, whatever. And we are placing those objects into our scene, right? And we also have a camera. And the camera has a camera position, right? And it needs also to have like a certain orientation, okay? So usually the way we define the orientation of a camera is not by directly, or the way we ask the user to define the camera is not by asking the user directly what is the actual rotation from the camera, because that, think about it, that will be very hard for a user to define, right? If this is, for example, inside Blender, Maya, or Trees to the Max, or whatever software you want, and you're asking the user or the programmer, you're asking the user to give you exactly the rotation, the rotation matrix on X, Y, and Z from the camera, we as humans, it will also almost be impossible to actually define that rotation, right? I mean, I can maybe trying to like experiment, like rotating the camera and see what the camera is seeing, right? Like try and error, but that will be crazy, right? So usually what you have is we ask the user to define a position for the camera and a position for a target, okay? I mean, in reality, in computer graphics, in again, Maya, 3 Studio Max, Blender, there are also there are two types of cameras, target cameras and free cameras. And sometimes we actually do need free cameras, basically cameras that are so for example, a free camera can be attached to a vehicle, right? Imagine that it's similar to a movie, right? So maybe imagine like a camera that is attached to a vehicle like a GoPro. So basically that camera doesn't have a target, right? That camera is basically inheriting all the position and orientation from maybe a vehicle, and then you just moving your vehicle and the camera is recording everything. In that case, you need a free camera. But usually what you need is a target camera from which you define two objects, the camera position and the target position, right? It's easier to define it like that. Okay, so you have a camera position and a target position, and basically from that, you get a vector that is usually called the gaze direction or the look at vector, okay? And basically this is just taking the target position minus the camera position, right? So it's very clear. It's just the direction of the camera, okay? And give me a second. Yeah. And by the way, in movies, I think this is also called the shot. Yeah, in Spanish we call it tiro. That is like shooting, like yeah. So in yeah, sorry, but I speak Spanish, but it's yeah. So in Spanish we call it tiro de la cámara, like the shooting of the camera. So it's basically like where the camera is aiming, right? Okay. So again, we have the camera, we have a target, and this world, right? It has its own coordinate system, right? So the coordinate system of the world is usually called WCS, which is World Coordinate Frame. And again, each of these objects here are a 3D mesh that maybe is coming from an OBJ file, and they also have their own coordinate system, right? Again, we already talked about this, but it's now we are kind of like seeing like a global thing, right? So these names right here are basically very common in computer graphics. So every time you hear someone's like or talking, oh, VCS, WCS, or OCS, they're talking either the object coordinate system, world coordinate system, and viewing coordinate system, and there are many names like that. Okay, so basically what we need right now is to compute the VCS, okay, the viewing coordinate system, because we have the world coordinate system, the object coordinate system, and now we need to compute this one. Okay, good. So the way we compute it, the first part is that we need to define this vector W that is usually in opposite direction from the look at vector, okay, and it needs to be normalized. Okay, so this vector W, that you will see that eventually it will be the equivalent to the Z axis of the coordinate frame of this camera, okay? But now we will call it W. We usually call it W when we were talking about cameras. It will be basically the position of the camera minus the position of the target and basically normalized, right? I'm here dividing by the length of this vector, right? And I said that this is usually pointing on the other direction from the look at, because this is how OpenGL works, okay? And this is super important. And again, this is just a convention. It could be either one option or the other, but remember that OpenGL and DirectX are basically the two most common technologies to render things in 3D, and they use different things, right? So for example, as you probably remember, OpenGL, we always use column vector notation, and in case of DirectX, they use row vector notation, right? So in this case, in OpenGL, the way the camera transformation is defined is that the Z value of the camera, which in this case we are calling W, okay, but the Z value of the camera is negative on the direction of the look at of the camera, Okay, so OpenGL uses negative Z, and this is basically following the right hand rule. You will see why is, I mean, when we compute the all the other vectors, you will see that is using the right hand. And in the case of DirectX, they use exactly the opposite. Their Z value from the camera is the positive Z value, and is pointing exactly in the same direction of the lookat. And they use a left hand notation, or left hand rule. Okay, and again, this is important because sometimes you can read a tutorial in internet that is basically based on DirectX, and you just mixing equations from one to another, and your code will be incredibly messy. Okay, so this is the first thing that we need to compute. Okay, then we need to define, or we ask the user to also define something that we would usually call up vector. Okay, so here actually we can see the three things that we ask the user to define to create a camera transformation. Okay, we will ask other things to create the actual projection. For now, for the camera transformation, we only ask for the position of the camera, the target position, or the position of the target, and also this up vector, right? So basically, what is this up vector? This is basically telling the vertical orientation of the camera. This is usually just a set unitary axis. So in this case, for example, I'm writing here up vector is equal to 0, 0, 1, right? It's always unitary. It needs to be unitary, right? But it doesn't need to be exactly on the set direction. So changing or modifying the direction of your up vector can help you, for example, to tilt your camera, and sometimes that is actually desirable. So and it has a name. So this is for example, this is an example of that. In this case, the camera in this picture I took on the, oh my god, what's the name of this park? The Stanley Park. So yeah, basically I rotated the camera, right? So the vertical axis of the camera is not exactly pointing on the Z unitary direction, right? This is called in movies and in computer games or whatever, this type of camera shot is called the Dutch angle, right? So and basically it's used to create like dramatic effect, right? So the way you make this type of like tilting is just by modifying the actual orientation of the up vector, right? So yeah, sometimes you can decide to use that. But for now, let's imagine that the up vector is just vertical, right? So the next vector we compute is the vector u, which is equivalent to the vector x from a coordinate frame, and we compute it as the cross product between the up vector and the vector w. Okay, and here you can see that again, every time you question like which orientation will be your resulting vector after a cross product. Remember that cross product, it's a right hand operation, right? So if you imagine your hand in which your thumb is pointing to the vector u, right? It means that your fingers, right, can like roll from the up vector to the w vector, right? So basically, depending on which order you use on the cross product is the orientation of the resulting vector in the cross product. So if you compute the u as w cross up vector, now the vector the vector u is basically pointing to the other side, right? But in this case, if we want to follow the OpenGL paradigm, the vector u needs to be on the right. Okay, so it will be always like this: the up vector cross w to get this vector. Okay, then we need to compute the basically the last part of the coordinate frame. Remember, a coordinate frame in the end is just a matrix that is composed by three basis vectors, right? So we have w, we have u, And we have another one, right? Because in this case, we cannot use up vector because it's not orthogonal, right? So if you are constructing a matrix that represents rotations, remember, that matrix needs to be orthogonal, right? It needs to be always orthogonal. It means that all the vectors need to be orthogonal between them. So you always need to perform several cross products. And so the next cross product is basically this one. We take, in order to compute the vector v, we need to take the cross product between w and u. And again, this is following the right-hand notation. And this is how we compute the entire this entire system. So now this coordinate frame, it's called VCS, which is the viewing coordinate system. And what it represents is its origin represents the position of the camera, and the tip of its basis vectors represent a rotation matrix that is basically representing the orientation of the camera. And this entire way of computing this thing is usually called a lookat transformation, right? And again, you will see later that we will also use this for inverse kinematics. Okay, and yeah, and last thing that I want to say is this camera transformation, something that is also important is that it needs to be, or it is, a rigid transformation. I don't remember right now, but I think I haven't told you the meaning of this concept of rigid transformations. So whenever you hear that in computer graphics, a rigid transformation is basically a transformation that is either translating objects or rotating objects, but not scaling, not skewing, not any other weird transformation. It's only rotation and translation, right? And we call those type of transformations, we call them rigid transformations. And basically they are the most similar transformations to what we see in real life, right? Because in real life, we cannot like stretch things unless they are made out of rubber, right? We cannot stretch or skew things, right? So we usually just move and rotate. Okay, so we can make a small pause right now. So to see if you have questions, and Nam is raising hand, perfect. Okay, so
Hello.
hello.
So just to be clear, the clear difference between the u vector and the up vector is that what I get is the up vector is the x-axis rotation in the view coordinate system, and the I'm confused as to why we need to redefine v when we have the up vector. Does that make sense?
Yes. Okay. Why do you need to compute v? You said.
Yeah, I mean, so I'm assuming that the up vector is user defined, so it's there in the beginning.
Yes, the u vector is user defined, exactly. But the thing is,
So that
the u vector is not necessarily orthogonal to u and to w and u, right?
you mean the up vector is not orthogonal to the
Not necessarily.
bottom two?
Not necessarily. I mean, it can be, right? If the camera, so for example, in this case, imagine that the camera is on the floor. The camera right now is not on the floor. But imagine the camera is on the floor and the target is also on the floor. It means that the vertical axis of the camera, it is also orthogonal to u and w, right? In that
Right.
case, up vector and v will be the same. But the thing is, you usually don't know, right? So what you get is just two positions: the position from the camera and the position of the target, and the up vector is defined by the user, right? So vector v, your third basis vector, because it needs to be orthogonal to the other two, you need to take the cross product again.
Okay, so based on what you said, the up vector is exactly the same thing as the roll of the camera, right?
The up vector is exactly as the roll of the camera.
The x-axis rotation of the camera. So
Yes.
with the same target position, you can just the only transformation to make the loop vector the same is if you rotate the camera sideways.
Yes. So
but
we could also say it like that, or like up vector is basically a rotated version of b.
Yeah, in the x-axis
in the
rotation
x-axis,
way.
which in this
Yeah.
case the x-axis is called u,
Right.
right? So basically that's why I'm using the same colors, right? So I always use red, green, and blue for x, y, z, right? So the x is the u vector, which is the red one, the y is the v, and then the z is the w, right? I mean, in many books actually, in many books, probably half of the books you will see the camera transformation and as xyz, and the other half of the books you will see them as uvw. Again, conventions and people just use different words, but it's the same. Okay. Anyone else with questions? You can raise your hand. If you have a question, please raise your hand. Okay, so let me read the chat because maybe people is shy. Okay, so Ken is asking, how do we find the right direction of V after taking the cross product? The right direction of V at... Oh, okay. So Ken, do you want to raise your hand and maybe talk? Because if you're asking, maybe I don't understand your question, but if you're asking how can we define the direction of B if it's either pointing up or pointing down, is that your question? Oh, okay, you're already broke. Okay, good. Okay, good question. That again depends on the order of your cross product operation. So remember, depending on the order of a cross product operation, you always get a resulting vector, right? So that vector is basically pointing to one side if let's say to the positive side if it's A cross B, or to the negative side if it's B cross A, right? So in this case, because you're computing W cross U, right? Imagine, yeah, I think next time I will draw a little hand here because I need to imagine that you have your right hand here and your fingers are pointing in this direction and your thumb is pointing into the V direction, right? So basically, if you imagine your hand like that and you close your hand, like saying, okay, I'm taking W cross U, right? Like closing your fingers from W to U, your thumb is pointing into this direction, right? So because you're using your right hand, it means that this operation will be pointing up, right? If you do exactly the opposite, if you imagine your hand doing exactly the opposite, open and your fingers pointing to the U and closing in the direction of W, if it's your right hand, basically your thumb will be on the other side. Okay. Any other question? Instructions on clear fingers work. Yeah. Okay. Now, another question. Yeah.
Hi, it's me again. So just to be extremely clear, so the user-defined parameters here is the up vector, but up vector and the look vector because the user is going to displace the camera somewhere, and that already defines all the necessary degrees of freedom for the camera. So what you essentially do is just transform the user-defined parameters into the coordinate system.
Yes.
So that's how I understand.
Yes,
Okay.
yes. Again, you get from the user, you get position of the camera, position of the target, and the up vector. Yes, Tommy. No, you're muted. Tommy.
Hello.
Yeah, hello.
Hi. When you answered Nam's question regarding the up vector is related to the rotation of the camera on the x-axis, it seems to me that we're then only able to rotate the camera in kind of like just the x-axis. So how would we tilt the camera in the other axis then? Or am I like kind of misunderstanding how the camera is rotating?
Okay.
Yeah.
The thing is, the rotation of the camera, if we are using this paradigm of using a target camera, right? Because we are using a target, right? The rotation of the entire camera is basically defined either by the it's by the position of the target, right? Because if you change the position of the target, you're basically changing the look at vector, right? And all your operations will be a bit different, and basically your basis vectors will change, right? So basically, just by moving the position of the target and by defining either this same up vector or a vector with different rotation, you rotate the camera, right? So if you, for example, if you instead of using a unitary z axis for the up vector, imagine that you are defining the up vector as I don't know, if you are like rotating the up vector, right, in a different rotation, what you will see is that the camera will keep seeing the same point, right? So it will keep shooting at the same direction, but it will just start to tilt, right? So if you modify the up vector, for example, imagine that we are animating the camera. If you animate the up vector, if you start to like rotating the up vector, what it will happen is that, again, the camera will keep seeing exactly the same point, but it will just start to rotate in the look at axis. Is that clear?
Yeah, thank you.
Good, perfect. Any other question? Can I keep going? Okay, I think nobody else has questions. Good, okay. So let's continue. So from that, right, now that we have defined these three basis vectors, and I said that in basically half of the books, they will call them U, V, and W, but it basically, they're exactly the same as the X, Y, Z from any other type of matrix that we have done before, right? So basically the transformation matrix of the camera is basically a multiplication of two different matrices, right? One is the translation, which contains basically the position of the camera, right? So the camera X, Y, and Z, and this is a translation matrix. Again, we are always using affine transformation matrices. So it's 4 by 4. This is the identity part. This should always be 0, 0, 0, 1. And this is the translation part. And it's basically needs to be multiplied by its rotation. And its rotation is just a orthogonal matrix composed by these basis vectors. So this is the basis vector red, right? That is what we are in this camera transformation. We call it U, V basis vector, or W basis vector, right? Is this clear? That these will basically create the transformation of the camera? A rotation times a translation. It's clear, right? It's exactly the same, because in the end, what we are doing here is treating the camera as an object, as any other object. If we have a bunny or whatever in our 3D world, we will do the same, right? We will compute the translation and the rotation. Okay, good. So basically, if you multiply that, you get this, right? So basically, this is in the end how does a camera transformation looks, right? Okay, good. I think it's clear, right? So say yes if it's clear. Perfect, good. Okay, so now I have a question for you. Now that you have a matrix for the camera, let's see what happens. I have my entire scene right here, and I have objects that they have its own coordinate system. I have the world that it has its world coordinate system, right? So imagine for a moment that you already transform the coordinates from basically your object coordinates or your model coordinates. You already transform them into world coordinates, right? So for example, let's imagine for a moment that this is a unitary box, and that this box in its own coordinates, basically these coordinates here are just 1, 1, right? However, if it's already transformed in the world coordinate system, it means that, for example, this corner here, it probably has like minus 0.8 probably, and let's say minus 0.8 and minus 0.8 in world coordinate system, right? Because now this point here with respect to the world has, yeah, roughly those coordinates, right? Okay, so now how can you translate from the world coordinates system to the camera coordinate system? What do you need to do? What do you think? Yes, Gloria, we need to the projection matrix. Yeah, but what do you think? Okay, Nami is saying that the what? Oh, now he's saying that he needs to multiply the inverse of the matrix from the object. So the inverse from the object matrix times the camera matrix. Okay, move to camera to, okay. Okay, let's see what happens. Or let's see what we need, because I think nobody is actually getting the answer. Again, what we need is basically we need to compute, we need to translate, to make like a conversion from world coordinates to camera coordinates. Well, we need to get this point right here, for example, that right now we have coordinates with respect to the world. We need to get now the coordinates of this point, but with respect to the camera, right? So what we need is we need the inverse of the camera matrix. It is clear why we need the inverse and not the actual matrix. If it's not clear, say no. Perfect. That is what I was expecting, that it was not clear, because yeah, it is usually not clear. Like, why the inverse? Okay, so now we need to continue with that part. So let's make a quick stop to understand when do we need the inverse, right? So we already talk about this, but this is very confusing. It is always confusing. It sometimes is even it is very confusing even for me and for every professor you whatever want, because it is confusing. Yeah. So basically, when you have different coordinate frames, depending of what you are asking, is if you are translating from A to B or B to A, right? And is this thing of you either need to use the actual matrix or the inverse of the matrix. So let's see if I can finally explain or finally give you an example of this. Okay, so imagine this. We have two coordinate frames, A and B, right? And in this case, A is kind of representing the world, right? Because basically the grid is aligned with A. So let's, for a moment, imagine that A is like the main coordinate system, okay? And we have a point P, right? So in this case, what we need is to get from A to B, right? And we will see why we need in this case is when exactly the moment in which we need the inverse. So basically what I want is for you to imagine that this is like saying, hey B, right? This is like coordinate frame A is calling coordinate frame B and saying, hey B, tell me the coordinates of this point on your coordinate system, right? So basically what we have here is A has a point P, which has coordinates with respect to A, that's why it says PA, 5, 1, okay? So I am A, I have 5, 1, these are coordinates of P, right? But now I want to know the coordinates of this point, but in the world of B, right? In B world, okay? So again, it's like asking B to tell me the coordinates of this point that I have right here, but in its own language. This is kind of like a conversion or translation, but not translation in the terms of, I mean, the word translation, we use it in computer graphics when we define movement, right? But in this case, it's like translation from one language to another, right? So basically, two different coordinate frames is like saying that this is Spanish and this is Russian, right? So it's like translating from Spanish to Russian or Russian to Spanish, right? So when we are using the inverse of the matrix, what we are doing is basically like a translation from two different languages, okay? Because we have the coordinates on one frame, is like the coordinates in Spanish, right? And we want basically to know what are the coordinates of this same point, but now in Russian. But let's say that Russian is B, okay? So in those cases in which you are basically converting from one to another, right? I'm calling this A to B. In those cases, you need to use the inverse of the matrix, right? So B is basically, I'm putting V as the coordinate system B, right? Or the matrix B. And you basically need to multiply the inverse of the matrix that is composed by these basis vectors times P PA, which is basically are the coordinates of this point in coordinates from the in Spanish coordinates, right, or in coordinates of the world A, right? And Khan is asking, what is the inverse of Russia? I have no idea of the inverse of Rushdie. Okay, so the other option, right? The other option is when we are going from B to A, okay? And this is more similar to a transformation. So one option or one way is similar to translate between two languages. The other way is more similar to actually transforming or moving or rotating things. So this is different, and the question is different. In this case, the question is something like, hey B, could you move this point to your 1, 1 coordinates? So imagine that, again, I have coordinate frame A, and it has a point B with coordinates 1, 1, right? So in this case, I'm asking a different question. I'm telling B, right, to move this guy to its own 1, 1 coordinate, right? You see? So now the 1, 1 coordinates of B is actually, so look, this is the basis vector I, right? So this is 1, 1. This is 1, 1 for B, right? But in this case, what I'm asking B is not giving me basically it's like, give me a new point, right? So that's why I'm in the drawing, I'm basically modifying the drawing, and I'm showing that you have point P, and after this transformation, you basically get a new point, right? Which is P prime. Okay. So is this more clear? Finally, like, when do we need to use inverses and not? Yes, Tommy, I can hear you.
Just to clarify, the point P's of B is corresponding to P prime of A, right? In the picture.
Yes.
Okay, cool. Thanks.
P prime of A. Well, okay. Give me a second. You mean here, right? Okay, so PB here is basically these coordinates. So PB here is basically 1, 1. Why? Because I'm asking B to compute its own 1, 1. That is in the end what I'm saying, right? I'm asking B to compute its own 1, 1. So that's why I'm saying, hey, B, could you move this point to your 1, 1, right? So this will be 1, 1, and this will be the matrix, right? And again, this when we do this from B to A, what we are doing is basically either rotating or moving or whatever. We are transforming the world. We're transforming those coordinates. But in the other case, it's different. In the other case is like, okay, the point is not moving. Conceptually speaking, it's like the point is not moving. I'm just asking what are the coordinates of that point, but now in this different language, right? So again, one way is like converting from one language to another. The other way is like getting a new position or getting a new transformation. Okay, good. So I hope that is clear. And so it means that if we want to actually compute the new coordinates, but not translating from or converting from word to camera, we need to get the inverse of this matrix, right? How can we compute that? Can someone tell me like the easiest way to compute the inverse of this thing?
MATLAB.
MATLAB, yeah, that is an option. But again, you need to see what you have, right? So we said that basically this transformation, this matrix transformation from the camera, is actually composed by two different transformation matrices, right? And one is a rotation matrix and the other one is a translation. We already said that inverting rotation matrices is actually very simple, right? Because this is orthogonal, right? And what about translation? How do you very quickly get the inverse of a translation? So yeah, many people is already saying transpose. Yes, so for rotation it will be the transpose, right? So here's a hint, right? So the inverse is transpose for orthogonal matrices, right? If it's orthogonal, the inverse is just the transpose. And in case of translation matrices, the inverse is just the negative, right? So that's why it's super easy to compute the inverse of these two things, right? Because this is just transpose, this is just the inverse. You multiply those and you get the inverse of the camera. And voila, you can basically convert from one to another. And people saying Math 2 was literally 4 years ago. Yeah, I understand, guys. If I told you what was my last algebra course, it was probably before you born or something like that. Okay, so good. So now, final question before we end this lecture. What do you think about the world coordinate system? Do we need the inverse when computing the coordinate system for the world coordinate system? And yeah, Pavel, Cx, Cy, Cz is basically the x, y, z from the position of the camera. So it's like camera x, camera y, camera z. So think about it. What happens when we get the world coordinate system? So we said that when we are translating from word to camera, right? We need the inverse of the matrix, right? The inverse of this matrix. But what happens when we are actually computing from model to world to world? What do you think? You will need to think about it. Okay, so Garrett is saying not inverse. Why not inverse? Are we asking a different question when we are transforming from object to world coordinates? Remember, one type of question is to ask like a translation between two languages, right? The other thing is literally transforming or moving things. So the answer is correct, Garrett. We don't need to take the inverse because it's a different operation, right? So basically what happens is that when you get, for example, this OBJ file, right, and you have your coordinates of your 3D model, when you move your 3D model in your scene, what you're basically creating is you're creating a transformation matrix for those points, right? So you will create, let's imagine that it has some translation and rotation, right? So basically what you have is you have points that originally were, they had originally a certain coordinates, right, in its own world, right? And you multiply those coordinates times this transformation matrix. And basically what you're doing is you're not asking for translating from one word to another. You are literally asking for a transformation because what you want is actually to move and rotate this object, right? So in that case, what you get is basically you multiply your original positions times the actual rotation or transformation matrix that you want for moving or rotating this object, right? And that gives you the new coordinates now in world coordinate system, right? So it's direct. You don't need the inverse. And when you compute now from world to camera, you need the inverse of the camera because all the things that I'm already said. Okay, good. So we need to finish for today. So the next lecture, we will keep talking about this because camera projections, they take a lot of time because they're very confusing. So we will probably keep talking about orthographic and perspective projections. If we have time next lecture, we will probably start to talk about clipping. If not, we'll basically need to like move a little bit our lectures. Don't worry because we still have time, and I set enough time between lectures. And yeah, so, and super important for our next lecture, this is not anymore a suggested reading. Now it's a required reading, right? So please read chapter 6 from book 3. Remember, everything is on the webpage. All the links are on the webpage, and yeah. So now it is a required reading. And if you have one question, I think we have maybe like 1 minute for one last question. Yes, Nam.
Okay, so I have two questions really. So when we were talking about inverting in the 2D toy examples, we are treating A as the world coordinate frame. So A is always fixed, and when you write the matrix B, the basis of B is defined in terms of A's coordinate system, right?
Yeah.
Okay, so just to be clear, the the camera transformation matrix is basically, or sorry, the VCS basis is written in terms of WCS. So that's why multiplying the coordinate of object in camera coordinate system by uh, the VCS basis will give you the world coordinate, and therefore inversing MCAM will give you world to camera. So I think a lot of people had that like backwards because sounds like multiplying by MCAM will give you world to camera, not the other way around.
Yeah, you're right. Good. Yeah, maybe David, last question.
Yes, I have a question about the slides. On the like I remember like when you first introduced this thing on the September 23rd, you have a slide that's similar, shows some similar thing like transforming from B to A,
Yep.
which you have a position of like a PB and you somehow change to PA.
Yeah.
But you didn't use the inverse there. I'm not sure like what's the difference.
It is exactly the same. If it's it is exactly the same. I mean,
like you only have one P. You didn't have two P, and it didn't end up with two
yes,
P though.
that is true. That what happened is in those lies I didn't draw the second P, right? Because what I wanted right now is to show you that in one direction is like translating from one language to another. So it's like you keep the same point and you're asking just the different coordinate frames. But if you are asking in this direction from B to A, when you don't need the inverse of the matrix, what you're doing in the end is just transforming the position, right? So you have a original position and you get a P prime position, right? A new position. So I think probably the only difference, conceptually speaking, the only difference between those slides from the past lecture and this one is that basically on the past slides I didn't draw the new P point, but conceptually
But
and mathematically speaking is the same.
Yeah, but the two P actually ends up at the same position though. Like,
Sorry again, what?
Okay, maybe I'll ask on PS because the two P actually ends up at the same position. It's like you say they're translating from one language to another. The two P actually ends up at the same position where you like the example shows there.
Like here.
No, not. I'm not saying about this question. I'm referring to the slides on the 23rd.
Oh, I see. Okay, yes. Yeah. Maybe I made a mistake. I mean, I'm 99% sure that is not the case. But yeah, maybe there's something that is, or maybe there's not a mistake.
Yeah, maybe it's just something I don't understand.
Yes, or maybe it's not clear enough. So yeah, so please post your question on Piazza. I'm sure that TAs can help us to get that, and yeah, and if it's not clear, I can maybe talk about this on the next lecture, right? But yeah, we need to finish for now. Okay, thank you so much, everybody. See you on Wednesday. Bye.